Hi everyone, my name's Aman and I'm the GCSE Chemistry tutor for the online school. Today we'll be looking at fractional distillation of oil and hydrocarbons. So we're moving on to organic chemistry this week, specifically looking at alkanes, alkenes, carboxylic acids and esters. I will try and cover all the exam boards and hopefully we'll have an interactive quiz to do today as well. If you've covered some of my lessons with me before, you'll know that we've been looking at quantitative chemistry and also things like bond energies and rates of reactions over the past couple of weeks. So today we are moving on to a different topic. As I said, my name's Aman. I study medicine at King's College London and I've done over 150 lessons with my tutor. Today's session will run for an hour from 2 until 3 o'clock. And as usual, if you have any questions at all, just pop them into the chat function or the Q&A box, and hopefully I'll pick them up as we're going along. So you won't need a calculator today. It will all just be through questions that I ask on here. So first of all, I'll go through the learning objectives. So the first learning objective is that we need to know what crude oil is, and we need to be able to draw, name and predict the alkane structures. So for all three exam boards, they want you to be able to draw, name and predict them using the general formula for them. And the ones that you need to be able to draw are the first four. So that's methane, ethane, propane and butane, which we'll be going into more detail with further on in the lesson. We then need to be able to explain the process of fractional distillation of crude oil. So again, if you've been with me before, a couple of weeks ago, we looked at separating mixtures and we did cover fractional distillation of ethanol and water. So today we'll be looking at specifically crude oil, and then we need to know the properties of hydrocarbons. Yes, today I do have a quiz. So the first thing we will be doing is a recap quiz from last week. So I'm just going to get that up now. So if you all go to joinmyquiz.com and put in this code, we should be able to play a recap quiz of things that we covered last week. So it will be on rates of reactions and collision theory. It's just a quick 4-question quiz. So if you go to joinmyquiz.com, put in this game code, we should be able to start it. And I believe if you can't join it, you should be able to see it on the screen. So you can send me in answers on the chat function if you can't join it, but hopefully you should all be able to join it. I think you've used this software before in another lesson. So I can't see that anyone's joined yet. If someone could put a message in the chat function to let me know if they are able to join, that would be quite useful because I've not used it before. So yeah, I know you've used it in physics. So, okay. You shouldn't need to register. I think you should just be able to join. Okay. Yeah, the link's on the screen. It's joinmyquiz.com. The code you need to enter is 329402. Okay, for the people that it says they need to register, that's fine. We'll play it on the screen. Hopefully you'll be able to see the question. So I'm going to start the game. Hopefully there's enough people in there. It's saying no one's currently in the game, so that's not helpful. Okay, fine. I'm not sure what's going on, so we'll have to leave the quiz. In that case, I'll just ask the questions there. I know some of you said you've joined, but it's saying that you aren't in it. Let me see if I refresh the page, what happens. Oh, okay, hold on. I can see some of you now. Okay, that's great. Can anyone else join? Okay, so we've got a few more people joining. We've got 6 people currently in it. I'll wait 1 more minute and then we'll start. So the link is just joinmyquiz.com. Okay, I'm going to start the quiz now. So for anyone that couldn't see the questions, first question's on the screen now. So it was asking about the effect on the position of equilibrium that increasing temperature would have on a positive enthalpy change reaction. Yep, so you can send answers here if you can't access it, so you should be able to see the question on the screen. So does anyone remember what happens when we've got an equilibrium, we increase the temperature, and we've got a positive enthalpy change reaction? Does anyone remember what does that mean? So positive enthalpy change means that it's an endothermic reaction. So if we increase the temperature, as someone has just said, it favors the forward reaction. So well done, because when we increase the temperature, the system wants to decrease it. And the only reaction that decreases the temperature is the endothermic reaction. So it will favor the forward reaction. The second question is, where does the position of equilibrium move if the pressure is increased in the following reaction? What do we think? So we can see, what do we do there? So actually the position of equilibrium doesn't move in this case, and that's because there are 2 moles on the left, so 1 mole of hydrogen, 1 mole of iodine, and 2 moles on the right. So for those of you that got it incorrect, the reason is because there are an equal number of moles of gas on both the left and the right, so the position of equilibrium doesn't move. The third question, how does an increased concentration affect the rate of a reaction? So what does an increased concentration do to the rate of reaction? Does anyone remember there? Anyone that's not answered on the quiz, if you want to send me in the chat box, you can do. So if not, an increased concentration will increase the frequency of collisions. Excellent. So people that are saying D, well done. So it increases the frequency of collisions, and that's because there are more particles in the same volume. And then the final question, what would happen to the position of equilibrium if hydrochloric acid was added to this reversible reaction? So this is a higher tier question. And if you remember last week, we went through what happens when you add hydrochloric acid. You're essentially adding hydrogen ions. So if we have a look at this reaction, there aren't any hydrogen ions there, but we have hydroxide ions on the product side. We have calcium hydroxide. So when we add the hydrochloric acid, the hydrogen ions will react with the hydroxide ions in the calcium hydroxide and effectively use them up. So if they use them up, we want more calcium hydroxide, in which case the position of equilibrium moves to the right. So the correct answer to that one was that it moves to the right. Well done to the people that said A. That's excellent. Okay, so that was a quick recap of last Friday's lesson and last week in general. So if you do have any questions about that, either send them in the chat box, or you can look at last week's lessons to go over that in more detail. I'm not sure who came first, sorry. I'll have a look at that at the end, because hopefully we'll do another quiz at the end. Someone's saying they don't understand. Do you mind sending a question as to what you don't understand? Yep, so can I please explain the change in the position of equilibrium? Sure. So the 2 questions that we had on the screen about changes in position of equilibrium. The first one was at the bottom, was about hydrochloric acid being added to the reaction. So when we add hydrochloric acid, we are essentially adding hydrogen ions. So I'll go back to here and I'll talk about it. So when we add hydrochloric acid, we're essentially adding hydrogen ions. And so when we add hydrogen ions, the calcium hydroxide that was produced gets used up. And that's because hydrogen ions react with hydroxide to produce water. So it's a neutralization reaction. And so when they react with the hydroxide ions, they get used up. So we want more calcium hydroxide, so the position of equilibrium moves to the right. And then the other question on the pressure, remember the pressure, if we increase the pressure, the system wants to decrease it. So to decrease it, it moves to the side with fewer moles of gas. In the question that I had up, it was hydrogen and iodine reacting to produce hydrogen iodide. And remember, when that reaction takes place, because there are 2 moles, 1 mole of hydrogen, 1 mole of iodine on the left and 2 moles on the right, they are balanced, so the position doesn't move. And then the final one was about temperature. So someone's asking me, I wasn't here when we went through this. As I said, I've not got time to go over this all because it's what we covered last week. So today we are focusing on organic chemistry. If you do need some more help on this, please have a look at the YouTube videos. They should all be up by now. So it was Thursdays and Fridays lessons that we went over kind of rates of reactions, Thursday and Wednesday's lessons that we went over rates of reactions and equilibrium in lots of detail and did lots of questions there. So hopefully that will make sense. So if we start with crude oil then, first things that we need to know is that it's a finite resource. What does finite mean? Does anyone know? What does finite mean? Yep, it will run out. It's not renewable. Excellent. So crude oil is an example of something that is finite. It is going to run out at some point. Brilliant. So first of all, we need to know how it's produced. And the main way that it's produced is from something called plankton. They are tiny organisms which were buried in mud and died millions of years ago. And when they were buried in the mud, over the years, lots of rock and other layers were laid on top of them. And what that meant is that all those plankton underneath were put under a lot of pressure. And as well as that pressure, because they had so much rock on top of them, it was almost like lots of insulation. So that produced high temperatures for them. And the other thing it did was kept out any oxygen. So if you imagine we've got these tiny little organisms buried deep in the earth, and then suddenly they add lots of rock layers on top, like so, it's going to create a lot of pressure on these tiny organisms and lots of insulation, which creates high temperature, and also it keeps any oxygen out. And they're the conditions that are required to produce crude oil. So that's how crude oil was produced, essentially. And the other thing we need to know is that it's a mixture of hydrocarbons. So does anyone remember what the definition of mixture is? So again, we went through this a couple of weeks ago when we looked at separating mixtures, but does anyone remember the definition of a mixture? Someone said physical bonding, exactly. So there's no chemical bonding in mixtures. Good, that's one part of the definition. Does anyone remember the second part of the definition? Oh, brilliant. So someone said 2 or more elements or compounds not chemically bonded or combined. That's amazing. That is the correct definition. For all examples, that's the definition for a mixture. So 2 elements or compounds not chemically combined. So 2 or more elements or compounds not chemically combined. What about hydrocarbon? What's a hydrocarbon? Does anyone know? I'll give you a clue. It's all in the name. So hydrocarbon. Good, yep, so someone said a compound made up of only hydrogen and carbon, and that's exactly correct. So a hydrocarbon is essentially just made of carbon and hydrogen, nothing else is there. So we need to know that crude oil is a mixture of hydrocarbons. And what does that mean? If it's a mixture, why do we separate it then using fractional distillation? What does that help us to do? What does fractional distillation help us to do? Does anyone remember? So as I said a couple of weeks ago, we looked at ethanol and water, and we separated that using fractional distillation, and we went through the steps of it. So why can we separate it? Brilliant. So it's because all these hydrocarbons have different boiling points, and because they have so many different boiling points, that means we can separate them using fractional distillation. Excellent. So just as a quick recap of this slide, crude oil is non-renewable. It will run out at some point. It's formed from plankton, which are tiny organisms, and they've kind of been buried in the earth. Lots of rocks have been placed on top of them, which has created the 3 conditions to produce crude oil, which is high pressure, high temperature, and no oxygen, which is essentially anaerobic. So remember that another word for no oxygen is anaerobic, like so, anaerobic, and that produces crude oil. And then what the crude oil is a mixture of hydrocarbons, which is great. So the first hydrocarbon we'll be looking at today is alkanes, and then we'll be going on to alkenes tomorrow, but today we're looking at alkanes. And as I said, most of the compounds in crude oils are hydrocarbons, and one of the hydrocarbons that are most commonly found in crude oil is alkanes. So the second point on here says that they are saturated hydrocarbons. Does anyone know what saturated means in terms of hydrocarbons? Or even if you know the definition of saturated, that will help you to answer that question. So what does saturated mean? So for example, sometimes we say that a certain job is saturated, i.e. there are no more jobs in that sector. So what do we think saturated means? Okay, so someone is saying they've reached their limit. Good. So it is all about reaching a limit, essentially. And with hydrocarbons, specifically alkanes, it's about reaching a limit of how many bonds there can be. So I'm going to draw the first alkane, which is methane. Methane is the first alkane. And the chemical formula for that is CH4. So remember, it is a hydrocarbon. It's only formed of carbon and hydrogen. And what we can see is that the carbon is bonded to 4 hydrogens like so. And if you remember on the periodic table, carbon has 4 electrons in its outer shell. So that means it can share 4 electrons with hydrogen atoms. So it shares 1 electron with each hydrogen, and hydrogen only has 1 electron. So it forms a single covalent bond with each hydrogen atom. So that's methane. And what we can see is that each bond is used. So that is a saturated molecule. If I then draw the second one, which is ethane, does anyone know the chemical formula for ethane? So CH4 is methane. Does anyone know the chemical formula for ethane? Someone said C2H4. Nope, that's ethene. What's ethane? Someone's saying C2H8. Not quite. Brilliant. Someone said C2H6. Brilliant. So there are 2 carbon atoms and 6 hydrogens, and I'll show you how that's drawn now. So there's 1 carbon atom bonded to another carbon atom. It's a single bond. And then there's 3 hydrogen atoms as the other bonds. So remember, each carbon can form 4 bonds. So there you can see the 4 bonds of carbon and 3 hydrogen atoms. And that's ethane. And what we can see there is that if there was a double bond here, we would have 1 less hydrogen, because carbon can only form 4 bonds. So if I put a double bond in, what happens is that we have 1 less hydrogen. So this is an unsaturated molecule. Whereas when all the bonds are single, like it is in ethane, all the bonds are formed and we have 6 hydrogens. So being a saturated molecule, it means that all the hydrogens that can be formed in there are there, and that it is a single carbon-carbon bond. So most mark schemes want you to say that saturated means that there is a single carbon-carbon bond, and that there is a maximum number of hydrogen atoms bonded to those carbon atoms. Methane is also saturated because remember that carbon atom has formed 4 hydrogen bonds, so it's formed all the hydrogens bonds that it can form. So as I said, all the exam boards want you to know the first 4 alkanes. So does anyone know what the third alkanes is called? So we've got methane is the first one, ethane is the second one. What's the third one called? Does anyone remember? Good, propane. And what's the chemical formula of propane? Does anyone know the chemical formula of propane? Excellent, C3H8. Good, so it's not C4H8. C4H8 is alkenes. That would be a butene, essentially. It's C3H8. Great, so propane, C3H8. And if I draw that out for you, there are 3 carbon bonds. Remember, each carbon forms 4 bonds. So we've got 3 hydrogens on the first with 1 carbon bond. On the second one, there's only 2 hydrogens, and that's because it forms 2 carbon bonds. And then on the third one, there'll be 3 hydrogens. And again, that is a saturated molecule because all the hydrogens that can be bonded are bonded. So C3H8, and they're all single carbon-carbon bonds. And the final one, does anyone know what the 4th alkane is called? Brilliant, butane, okay? And what's the chemical formula for butane? C4H10, excellent. So butane is C4H10. So again, 4 carbon atoms now, all singly bonded. The last one over here can form 3 hydrogen bonds, and that's because one is formed with a carbon, so it has 3 bonds left. The second one can only form 2 hydrogen bonds, and that's because the other 2 bonds are with carbon atoms. The third one can also produce 2 hydrogen bonds, and that's because 2 are with carbon atoms. And the final one can produce 3. And if we have a count of the hydrogen atoms, we've got 4 here, 5, 6, 7, 8, 9, 10. So that brings me to my next question. You can see the chemical formulae for all of the alkanes, the first 4 alkanes, sorry. What's the general formula for an alkane? Does anyone know what's the general formula for an alkane? So if, for example, an exam question said to you, you've got an alkane, it has 12 carbon atoms. How would we work out the number of hydrogen atoms? What is the general formula? Good. CnH2n plus 2. Excellent. So the general formula for alkanes is Cn, and N just means a number of carbon atoms. H2n, so that means we double the number of carbon atoms, plus 2. So if we just look at ethane, for example, there are 2 carbon atoms, so that means N is 2. So that means we expect our hydrogen to be 2 times 2, which is 4, plus 2, which is 6. So that's why ethane is C2H6. If we look at propane, there are 3 carbon atoms, so that means the N is 3. So 3 times 2 is 6, plus 2 is 8. So propane is C3H8. And then finally, butane has 4 carbon atoms. So that means 2 times 4 is 8, plus 2 is 10. So this is the general formula for all alkanes. And that all alkanes will follow that formula. So as I said, in an exam question, if they tell you the number of carbon atoms, you can use this formula to work out the number of hydrogen atoms. So let's do that now. If I tell you that an alkane has 21 carbon atoms, how many hydrogen atoms does it have? Or what's the formula of that alkane? So it's got 21 carbon atoms. How many hydrogen atoms will it have? So remember, use the general formula to help you there. Okay, so we've got differing answers. It's always going to be an even number. Good, so someone has said C21H44. Excellent, well done. And the reason for that is if we use our general formula, C, I said, is 21. So that means that hydrogen will be doubled. And if we double 21, we get 42. And then if we add 2 to 42, we get 44. So C21H44. Excellent, well done. Okay, we'll do one more example. What if I say this time there are 17 carbon atoms? So 17 carbon atoms. How many hydrogen atoms are there? So 17. Okay, so we've got 36 hydrogens. Excellent. So 17 times 2 is 34. We add 2 and we get 36. So yeah, C17H36. Well done. Someone's asked me, why is methane saturated? As I said, methane is saturated because it's formed all the hydrogen bonds with carbon and there are no double bonds in there. So just a recap of this slide then, most of the compounds in crude oil are alkanes. Remember, alkanes are saturated. That means that all the hydrogen atoms that can be bonded to carbon are bonded and there are no double bonds. The first 4 alkanes are methane, ethane, propane, and butane. The way that I learnt to remember that was using a quick rhyme, but someone has suggested a rhyme to me. Someone said, men eat proper burgers. So that's one. The one that I learned was many eat peanut butter. So I'll write those both on. So men eat proper burgers was what someone suggested. And I learned many eat peanut butter. So if you struggle to remember those, that's a nice way to remember them and will hopefully help you in the exams. But as I said, you just need to know the first 4. You need to be able to draw them, name them and have their chemical formulae as well. And you need to be able to predict other alkanes using the general formula CnH2n plus 2. Are there any questions on that before we move on to fractional distillation and the process of fractional distillation? Okay, great. So separating crude oil, we've already said that we do that using fractional distillation, and someone has already told me that the way we do that, the reason we do that is because all the hydrocarbons in crude oil have different boiling points, which is exactly true. So I keep referring to this example of ethanol and water, which is what we went through before. And that was because ethanol and water have different boiling points, which allows ethanol to distill off using fractional distillation so that we get ethanol in one beaker and water in another. And it's essentially the same thing when we separate crude oil. So we use fractional distillation. Okay, so I've got a fill in the gap exercise now for how we do fractional distillation. So let's have a go at trying to do this together. So crude oil is added into a what? So in what does fractional distillation take place in? Does anyone remember what it's called? What's that piece of apparatus called? So what is crude oil added into for fractional distillation to take place? That's the first two words. Not a distillation flask. Good try. Yeah, excellent. Someone said fractionating column. So what the apparatus is called a fractionating column. Good. So fractionating column. Okay. The next part says crude oil is added into a tall fractionating column as a hot what? So what state do you think crude oil is added in as? Does anyone know what state? Good, it's added in as a gas. So the specific word we use is vapor. And the reason we say vapor is that it might not all be a gas. So we say vapor. So remember the difference between evaporation and boiling. So boiling is when all of a liquid becomes a gas. Evaporation is when slowly that liquid turns into a gas, but not all of it has turned into a gas yet. So we say vapor. Someone's saying, but isn't the fractionating column where the glass beads are present? You're exactly correct. Yep. So there's two types of fractionating columns. There's the fractionating columns that we use in simple school experiments where you will have glass beads, but the crude oil fractionating column is a bit more extensive than that. You don't need to know much detail on it. The only detail you need to know is what's going to be on the slide once we've filled it in, but it is called a tall fractionating column because it simply relies on the same things. So there's still beads in there that allow the different hydrocarbons to boil off at different temperatures, or to condense off, sorry, at different temperatures. Okay, so we've done our first two. So crude oil is added into a tall fractionating column as a hot vapor. So as I said, it's essentially a gas. What do we know about the fractionating column? What is it at the bottom? What's the fractionating column at the bottom? I'll give you a clue. This relates to the temperature of the fractionating column at the bottom. Does anyone know what's the temperature at the bottom? Good, it's hot at the bottom. So it will always be the hottest at the bottom. So we'll say it's hot at the bottom. And so what does it become towards the top? If it's hot at the bottom, what does it become towards the top? Cooler, excellent, well done. So it becomes cooler towards the top. So currently we've said crude oil is added into a tall fractionating column as a hot vapor. So we vaporize it. And that fractionating column is hot at the bottom and it becomes cooler towards the top, which is exactly the same as when you do it at school and use the glass beads in a fractionating column. It will always be hotter at the bottom than the top. And the reason for that at school is that we use a Bunsen burner, and the Bunsen burner is always closer to the bottom. And the way that the glass beads are arranged, they allow for it to be cooler at the top and hotter at the bottom. So well done. What do the gases do then in that fractionating column? What do they do? Good, they rise. So they rise up, travel up. The best word to use is rise. So they rise up the column, and the what condense when they reach the temperature of their what points. So we know they're gases, so they're going to condense. Do you remember I said what crude oil is made of? What is crude oil made of? So the word here is what crude oil is made of. Hydrocarbons, excellent. So the hydrocarbons condense when they reach the temperature of their what points. So when does condensation happen? Does it happen when a liquid becomes a solid or when a gas becomes a liquid? And what's that called? Is it the melting or the boiling point? What do we think? What's that called? So at what temperature does something condense? Melting or boiling point? The boiling point, excellent, well done. So remember, melting point is solid to liquid, And boiling point is essentially gas to liquid or liquid to gas. And remember that it's the same temperature whether you're going from gas to liquid or liquid to gas. It's just coming from a different direction. So what I mean by that is that if we're heating a liquid up, it will become a gas, at a certain boiling point. The same goes for the other direction. So if I'm cooling a gas down, it will become a liquid at the same temperature as its boiling point when it goes the opposite direction. But because you're cooling it down, it becomes a liquid instead of becoming a gas. So it's about whether you're heating or cooling it. So it's a boiling point. Well done. Okay, so what leaves the top of the column then? So we know that there's a difference between the top and the bottom. So if the top's the coolest, what's going to leave at the top and what's going to leave at the bottom? Good, so gases tend to leave at the top of the column. So the gases will rise up. They don't tend to condense very well. They tend to stay as gases, so they will leave the top of the column as a gas. And at the bottom, you tend to get liquids and solids. Sometimes actually we call them kind of very thick liquids, which we'll go through in just a bit. But yeah, I'm going to put solids there just because they are almost solids. So you can say liquids or solids, but essentially they're very thick liquids. Good. Any questions about that? So I'll just read through it. So crude oil is added into a tall fractionating column as a hot vapor. So it's added in as a gas, which is hot at the bottom and it becomes cooler towards the top. Those gases will rise up the column and the hydrocarbons condense when they reach the temperature of their boiling points. So that means that hydrocarbons that have a lower boiling point will condense higher up, and hydrocarbons that have a higher boiling point will condense lower down, because remember, it's hotter at the bottom and colder at the top. And so gases leave the top of the column and solids come from the bottom of the column. Any questions on that? Otherwise, we'll move on. Okay, let's move on. Would a thick liquid be classed as a solid? So in exam mark schemes, they tend to accept thick liquid or a solid, and not quite. So a solid, it depends on the particle arrangement. A thick liquid is kind of on the boundaries between becoming a solid. So remember, liquids tend to flow, solids won't. So this is a really key slide where we're looking at the properties of hydrocarbons. So we're going to take our time and go over these carefully and make sure everyone understands, because there's some difficult words on here as well that you're expected to know. So I've already mentioned that the shorter hydrocarbons tend to leave at the top of the column. And that's because they have a lower boiling point. So remember, the top of the column is coldest. And so if they have a low boiling point, they will leave there. So that means they can rise up until they reach their boiling point, which will be at the top. Whereas the longer hydrocarbons, so by that I mean longer, say for example, if we think about a hydrocarbon that has 30 carbons, so if we think about an alkane, let's say, that's got 30 carbon atoms, and therefore it will have how many hydrogens if it's got 30 carbons? And we're thinking about an alkane, so if it's got 30 carbons, how many hydrogens will it have? Good, 62. So remember, you double it and add 2, so 62. And then if we think about another carbon atom that just has, another hydrocarbon that just has 5, how many hydrogens will that have if it's got 5 carbons? Good, 12, so double it and add 2, so 5 times 2 is 10, plus 2 is 12. So if we think about these two hydrocarbons, so we can see that this is a shorter hydrocarbon, it's only got 5 carbons, whereas this one over here has got 30. So the 5 hydrocarbon will tend to have a lower boiling point, which means it will leave at the top of the column, whereas the one with 30 will leave a bit lower down. So the next row talks about volatility. And volatility is about the ability of a hydrocarbon to become a gas. Any ideas why shorter hydrocarbons become a gas more easily? Why do shorter hydrocarbons become a gas more easily? Any ideas? Good, their bonds are easier to be broken. Yep, that's one good answer. Someone's saying less bonds to break and make. Yep, that's also a good answer. Anything else? Why are their bonds easier to be broken in shorter hydrocarbons? Why is it easier to break them? Anyone know? What makes it easier to break bonds in shorter hydrocarbons? Yeah, excellent. So someone's given me a great answer. They've said there's less intermolecular forces. So just as a quick recap of intermolecular forces then, because I know lots of students get confused about that. Let's just think about methane. So remember, methane is CH4, but you won't just find one molecule of methane. It will tend to be bonded together, but the bonding that you find between molecules of methane is called intermolecular forces. And what do people remember about intermolecular forces? So this must have been one of the first lessons we did. So does anyone remember what's special about intermolecular forces? Why is it then? So they're not proper bonding. Intermolecular forces are almost like attraction. So they're not chemical bonding as such. What do we know about intermolecular forces? Yes, they're easily breakable. And why are they easily breakable? So examiners don't like easily breakable. They like a specific answer. They are weak, but what does that mean? What specifically about intermolecular forces? What do we need to say in an exam to help us answer why they have low boiling points, for example? Why molecules with covalent bonds and intermolecular forces have low boiling points? So we need to talk about it in terms of energy. So what we need to say is that there are weak intermolecular forces between molecules of hydrocarbons, and therefore very little energy is needed to overcome those forces. And it's really important you don't say break the forces, because those forces aren't really there, they're attractive, so you essentially overcome those forces. So the reason that hydrocarbons that are shorter become gases a lot more easily is because there's those weak intermolecular forces between those molecules. And that's why they become a gas very easily. So on the other side then, longer hydrocarbons, it tends to be harder for them to become gases, and that's because we need more energy to overcome those forces. As I said, try not to say break, say overcome those forces to help us answer that. Okay, the next word then that we need to know is viscosity. So viscosity is about the ability of something to flow. And essentially, if something has got low viscosity, we say that there's not much friction there, and therefore it flows really easily. So something that's very runny will have a low viscosity and it flows really easily. So if you imagine a glass of water, if you spill that glass of water, that water will run really easily. Whereas if, for example, you imagine quite a thick smoothie, that smoothie is not going to flow as easily, and that might be because there are chunks in there that break it up, but also because it's a lot harder for it to flow. So it's the same with short and long hydrocarbons. When something is shorter, if you imagine a chain, that chain is less likely to become tangled up, and therefore it will tend to be fine as it is and will flow. Whereas when we have a longer hydrocarbon, say with 30 carbons like the one we have above, it's more likely to become tangled, and that means it's more likely to be thicker and it's harder for it to flow. So the reason that shorter hydrocarbons are very runny is because they've got lower boiling points and there's less energy required to overcome them, so they are more likely to be able to move easily. It's essentially because they are shorter. And therefore they're less likely to kind of become tangled. You don't want to say tangled in the exam, that's just an example to help you understand that. All you need to talk about is the boiling points being lower. And same with longer hydrocarbons, the boiling points are higher, and so they have a higher viscosity, they tend to be thicker, and it's harder for them to flow. So the last property that we need to know about is flammability. And flammability is about the ability of something to burn, specifically in oxygen. And we say that short hydrocarbons have high flammability, which means that they burn really, really easily. And we are going to be covering that tomorrow when we look at the burning of alkanes. And longer hydrocarbons tend to have low flammability. And that means they find it difficult to burn, and they tend to burn with what we call a smoky flame. So a smoky flame means that it's going to be more sooty, have a lot more black in it, and it's not going to be as clean of a flame. So any questions on that? Any questions on the properties of hydrocarbons and the differences between short and long hydrocarbons? Because it's really important that we understand this and we can answer questions on it. They're quite common exam questions. So they'll either give you two hydrocarbons to compare, or they'll ask you for the meanings of volatility and viscosity. So any questions that you have, please ask them, because I'm more than happy to answer them for you. Okay, so the final thing we need to cover then is essentially about what comes out of the fractional distillation column. So someone's asking, why do shorter hydrocarbons have a lower viscosity? So as I said, low viscosity means that they are runny. It's because they have lower boiling points, so there's less energy required, and also because they're shorter, essentially it's easier for them to flow. If they were longer, if you imagine it's a longer chain and therefore it's much harder for it to flow, it tends to be thicker, and it's to do with the boiling points between the atoms. Essentially there's more flexibility when it's got a low viscosity, but not when it's got a high viscosity, so when it's longer. Okay, so as I said, the final thing we need to know about is the fractionating column, and someone's just asked me what is the top of the fractionating column, and that's a really good question, and I'm going to show you that now. So the top of the fractionating column is here, and what we can see is that it's cooler at the top and hotter at the bottom. So in comes our heated crude oil, so it's a vapor essentially, and we've got 6 fractions that come off, and these fractions we do need to know about, and we need to know about their uses. So any ideas, what's the top fraction? Does anyone know what the top fraction is? And it's okay if you don't, we'll go through it together, but does anyone know? Nope. So I know we spoke about alkanes. These aren't essentially alkanes that are coming off. They have specific names, which we're going to go through. So someone said gases. Good. So the top that comes off, we call it petroleum plus refinery gases. So petroleum plus refinery gases. And essentially they are used as fuel gases, and they're called fuel gases because they are gases. So they're used in fuels that need gases. So they're fuel gases. So that's their kind of use for it. So I'll put fuel gases. Okay, any ideas for the second column? I'll give you a clue. This is used in cars, as a fuel in cars. So if you go to a petrol station, there's 2 types of fuels. I'll give you a clue. It's one of those. Good, it's petrol. Excellent. So it's petrol and gasoline that come off next. So petrol and gasoline. Petrol plus gasoline. So we're starting to become a liquid now. Petrol and gasoline, and that tends to be fuel for cars. So fuel for cars. There. Okay, what about the next one? I'll give you a clue. This starts with a K and it's used as aircraft fuel. Aircraft. Good, someone said kerosene. That's exactly correct, and it's used in aircraft. So if you think about the airplanes, it's kerosene, which is used for aircraft fuel. So the top one we said was petroleum and refinery gases, and that is used as fuel gases. Then the second one coming off, or the second fraction, was petrol and gasoline, and that's used for fuels for cars. The third fraction was kerosene, which is used as an aircraft fuel. The fourth column is the other fuel that tends to be for cars. So what's the other fuel? So we talked about petrol. What's the other one that you tend to find in a petrol station? Good, someone's saying diesel. Excellent, yeah. So the next column is diesel. And again, that's for cars. So you can just say fuel for cars. So fuel for cars. Okay, what about the next column? Does anyone know what comes in the next column? So this tends to be for ships. This is fuel for ships. Any ideas what tends to be used as a fuel for ships? So we've got petroleum, we've then got our gasoline and our petrol. It's not coal, so coal is another type of non-renewable source. It's not coal. What do we think? What could be used here? So I'll give you a clue. The top one was called refinery gases. If I tell you we've now officially become a liquid, so it's no longer a gas, what would we call it here? Good, fuel oil. Excellent. So someone said fuel oil. So yeah, refinery liquids or refinery oil. So it's essentially a fuel oil, and that's used for ships. So fuel oil is used for ships. And power ships and things like that. So that's to power them. And then the final one, this is when it does become kind of a very thick sludge. And we're thinking about roads. So does anyone know what we use to surface roads? Not tar, on the right track though. So it's called bitumen. So bitumen is the last one. So bitumen, and it's used for road surfacing and also for roofs. So road surfacing and for roofs. So the 6 fractions we need to know: petroleum and refinery gases at the top, petrol and gasoline comes off second, kerosene, then diesel, then fuel oil, then bitumen. Now there's a bit of a discrepancy between the exam boards here. So what I've noticed with AQA exam boards, they tend to ask you kind of what the fractions are used for. So for example, they might say, you've got kerosene, what's that used for? That's a really common one. So kerosene is one I would definitely remember, that it's used for aircraft fuels. Edexcel do tend to want you to know all of them. And OCR, again, they tend to be a bit like AQA and ask you for their uses. If I were you, I would try and learn all of them. They are in all the textbooks as well. So it's about knowing what comes off at the top. So the refinery gases and petroleum, and it's used as a fuel gas. The petrol and gasoline are used as fuel for cars. Kerosene, aircraft fuel. Diesel is a fuel for a car as well. So hopefully petrol and diesel are easier to remember, because you might have cars at home, or you've been to a petrol station, so you know what fuels are used there. Fuel oil tends to be used in ships, and then bitumen is always the last one for road surfacing. So either try and print that diagram out and try and fill it in yourself and until you can remember it, or if there are ways that you can think of to remember it, then try and use that. The way that I used to remember it was when I was revising for my exams, I had a filled in diagram and I kind of put it up in my room. And so every morning when I woke up, I would see it. And then after seeing it so many days, I kind of tended to remember it. And I did that with a lot of key diagrams. So if you think that's something that might help you, I'd recommend that. But a lot of my other friends tended to just practice doing the diagrams until they remembered it or kept reading it. But I think one thing that I would say is that you need to kind of keep seeing it or keep practicing it to help you to remember it, or find something that helps you to understand it. So either some kind of rhyme or something, or find a way that you can remember it through something like that. Okay, any questions on this before we do some exam questions then on this topic? Someone's asking for a link for the sheet. Yes, so I think this diagram was the diagram from BBC Bite Size, but there's one in all the textbooks and they tend to be really similar. So I think the one on BBC Bite Size is the most clear. So if you just go onto BBC Bite Size, AQA Chemistry, Edexcel Chemistry, and talk about the fractional distillation of crude oil, you'll see that diagram there. Or just type it into Google and they have loads of diagrams that just need filling in. Okay, so let's do an exam question or two then. So let me just get those up. All right, so this question is about organic compounds. Hydrocarbons can be cracked to produce smaller molecules. We're going to go through cracking tomorrow. So this question says, which product of the reaction shown is an alkane? So I appreciate that's a bit small. So if you can see that, which one over there is an alkane? Top one, this one, this one, or this one. For people that can't see it, the first one says C2H4, the second one says C3H6, the third one says C4H8, and the fourth one says C6H14. Good, the last one. So for the person that asked me before, why isn't one of the fractions methane? The reason for that is that when we do fractional distillation of crude oil, we still tend to get mixtures. So for example, the refinery gases tend to be mixtures of gases. So there's actually another process we have to go through to produce alkenes and alkanes, and that process is cracking, and that makes it into those individual components. So as I said, we're going to go through that tomorrow, but essentially all of crude oil is made up of hydrocarbons, not just alkanes, but they are mainly alkanes. So well done to everyone that said the fourth one. So the correct answer is C6H14. Okay, so this is a typical exam question. So the table shows the boiling point, flammability, and viscosity of C18H38 compared with the other hydrocarbons shown in the equation. Which letter, A, B, C, or D, shows the properties of C18H38 compared with the properties of C2H4, C3H6, C4H8, and C6H14? So for those of you that might be a bit confused, essentially this question is asking which one shows the property of a longer hydrocarbon, C18H38, compared to shorter hydrocarbons. So we've got a hydrocarbon with 18 and a hydrocarbon with 6, for example. Which one shows the properties? So with the one with 18, is it going to have a higher or lower boiling point? Is the flammability going to be lower or higher? And is its viscosity going to be higher or lower? Okay, so we've got lots of mixed answers at the moment. We've got A's and B's. Okay, so let's go through it together. So essentially, because it's a longer hydrocarbon, there's more intermolecular forces. They're a little bit stronger as you get longer as well. And so what that means is it's got a higher boiling point. So the people that are getting confused between A and B, that's right, because we've knocked out C and D based on the boiling point. So it's neither of these because the boiling point will be higher. Then we're thinking about flammability, and both of them say low. And that's true because we know that as something gets longer, its flammability, it's harder for it to burn. That's because more energy is needed. So it tends to burn with a more smoky flame. So that's right, the flammability does tend to be low. Then we're thinking about viscosity. So can someone remind me, what does viscosity mean? What does viscosity mean? Good, so how well it can flow. Yeah, you can think about it as how runny it is. So essentially, if it's got a low viscosity, so if we go back to this page here, if it's got a low viscosity, it's very runny. If it's got a high viscosity, it's very thick. So as we become longer, it becomes thicker, and therefore the viscosity becomes higher. So the correct answer is A. So well done to people that said A, and that's because the viscosity gets higher. So the person that said that viscosity is about how runny it is, yep, that's really good. Just remember that low viscosity means runny, high viscosity means thick, because it can be a bit confusing. But very well done to everyone there. Okay, so the next question here is also a very typical exam question. So first of all, you can see this is another fractionating column and gases come off at the top. The second one tends to be petrol, bitumen's the last one, and the other 4 there. So should we have a go at just quickly filling in the other 4 based on what we remember? So we said gases, refinery gases come off at the top. Petrol was the second. Does anyone remember the third column? What came off after petrol? Kerosene, excellent. Yep, so aircraft fuel, so kerosene comes off third. Good. What about fourth? What comes off next after kerosene? Good. Diesel, excellent. Well done. You guys are all remembering this really well. Okay, what about the next column after diesel? Fuel oil. Yep. And the next one tends to be bitumen. So they've put 4 more in there. That's okay. They do tend to split it up, but it is bitumen there. So that's absolutely fine. So the 6 you need to know are refinery gases, petrol, kerosene, diesel, fuel oil, and bitumen. Okay, well done. So this is, as I said, a typical exam question where we want to describe and explain how petrol is separated from the mixture of hydrocarbons in crude oil. So I'm going to help you to write a kind of typical exam answer to that then. But before we do that, does anyone have any ideas? So this tends to be a 4 to 6 mark question. All the exam boards want you to know about it. How do we separate petrol from crude oil? What's key to kind of go into that then? So in these types of questions, you tend to get marks for your English, although we do see less of these questions now in the new exam, exams. So what do we need to say about our fractionating column that's going to help us to answer this question? Good. Okay. So first thing we want to say is that crude oil enters the fractionating column as a gas or as a vapor. Yep, and the gases tend to rise up the column and condense at their boiling points. And what's really important here is that you refer back to petrol. So we can say that petrol has a lower boiling point than some of the other fractions, and so leaves the column higher up. And remember, that's because it's cooler at the top and hotter at the bottom. And that's it. That would be enough to get you all your marks. So it's just about describing the fractionating column. So we can also just say that the fractionating column is hotter at the bottom and cooler at the top. So you'll get marks for saying that crude oil enters as a vapor, that the gases rise up and they condense at their boiling points. So it's really important you say boiling points, not melting points. You get a mark for saying that petrol has a lower boiling point than other fractions, and that it tends to leave the column higher up, and that the fractionating column is hotter at the bottom and cooler at the top. So everyone that sent me answers, really good answers that we've had here. So yeah, so just make sure your English is quite good when you're answering it and it all flows quite well. But very well done to everyone that gave me answers. You're all correct. So someone keeps saying that I'm freezing. Is everyone having that problem? Am I freezing for everyone, or is it just one person that's finding that? Okay, that's fine. That's great. Okay, let's go on to a different question then. Okay, so again, it's a bit difficult to see. I'm sorry about that. So essentially, they've given you the formulae for hexane, octane, nonane, and decane. And if I tell you that hexane has 6 carbons and octane has 8, what's the formula for heptane? So this is C6. So this is C6, H14, and this is C8, H18. What do we think heptane will be? It's an alkane. Good, C7H16. Excellent, well done everyone. So heptane, C7, H18, 16. So remember, what's the general formula then of alkanes? So the next question here is asking for the general formula of alkanes. So C7H16 is correct, well done. CnH2n plus 2, well done. So it's a really key formula to remember. So CnH2n plus 2, well done. And I just want to say that remember these names here, hexane, heptane, octane, nonane, decane, they actually come from the same places that maths and your polygons come from. So if you remember hexagon, heptagon, octagon, it's all the same. So these are prefixes that we use and they mean a number. So hex is 6, hept is 7, oct is 8, nona is 9, and deca tends to be 10. So that's where it comes from, and all the hydrocarbons tend to follow that. So if anyone was wondering why the names are like that, that's where it comes from. Someone's asking if we can do another quiz. We will definitely do another one tomorrow. Yeah. So we will do that question. Okay, so crude oil is a fossil fuel. It's being used up faster than it's being made. So what problems will that cause for the future? So what do we think? 2 marks, we need to make 2 points. Crude oil is being used up faster than it's being made. What will that create problem-wise for the future? What do we think? Yeah, they're finite and so scarce, so there will not be enough crude oil in the future. Good. So that's 1. It may run out, meaning we won't be able to use it as a fuel. Good. So you can talk about not being able to use it as a fuel. You can talk about it running out. They'll give you 2 marks. You could talk about a greater reliance on renewable sources. So things like wind power, solar power. So they're renewable sources of energy. So we have to rely on those because crude oil will run out. Excellent. So well done everyone today. Tomorrow, as I said, we'll be looking at alkenes, esters, carboxylic acids, and going on to look at cracking as well. Hopefully we'll do another quiz at the beginning as a recap, but very well done today. Hopefully the exam questions helped you to understand and bring this topic together. All right, so I'll see you all, sorry, on Wednesday, not tomorrow. So I'll see you all on Wednesday at 9:45 in the morning. Okay, bye.